Hello, my name is Juan Mendoza, and I'm an undergraduate researcher in the Chow Lab here at Lehigh University. Today, I'll present my work titled Characterizing the Mechanical Properties of Solvent-Cast 3D Printed Biodegradable Polymer Constructs. Now, just as some background information, the Chow Lab focuses on fabricating modular biomaterials, specifically scaffolds that mimic the osteochondral interface, or cartilage, for functional tissue regeneration. This means that we are interested in fabricating polymer constructs, our scaffolds, that have biochemical and mechanical property gradients that replicate the natural gradient in the OC interface. This is important because we want to create a smooth transition from harder bone tissue to softer connective joint tissues. It's widely known that biomaterials' physical properties are critical in driving cell-material interactions. For example, human mesenchymal stem cells, or HMSCs, seated on stiffer substrates, promotes osteogenic differentiation, or bone cell growth. However, distinguishing changes in cellular response due to scaffold architecture and mechanical properties is difficult. It turns out that a scaffold's mechanical properties are pretty intertwined with its overall architecture. If you change one, you're kind of changing the other. Now, there are ways around this, but typically, decoupling changes in cellular response due to architecture and mechanical properties is difficult because they are interdependent. Our preliminary data showed that lower porosity, or smaller pores, promotes HMSC osteogenesis, while higher porosity, or large pores, promotes both chondrogenesis and osteogenesis. We hypothesize this effect is caused by differences in scaffold stiffness due to variations in porosity. This work aims to characterize polycaprolactone, PCO, scaffolds printed with different porosities to investigate how architecture affects stiffness. Figure 1 is a schematic showing PCO dissolved in the volatile solvent HFIP and extruded through a printer head. The HFIP evaporates, leaving behind a solid PCL filament. So this brings me to Solvent-Cast 3D printing. Solvent-Cast 3D printing allows us to specifically tune scaffold architecture, including the porosity of our scaffolds, by changing the spacing between each filament, also known as filament spacing. Higher porosity is characterized by larger pores. This is achieved by increasing filament spacing, and lower porosity corresponds to smaller pores, done by reducing filament spacing. To begin, PCL was dissolved in the volatile solvent HFIP at a ratio of 370 mg per milliliter. The inks were then loaded and extruded through a 32-gauge needle with a 100 micron inner needle diameter using a Nordson EV fluid dispensing robot. Figure 2A displays the Nordson printer head and needle. The printer takes custom codes for scaffold architecture. The following was maintained across all scaffolds: 15 mm by 15 mm by 24 layers, printed at a pressure of 70 psi, a first layer line speed of 0.4 mm per second, subsequent layer line speed of 0.2 mm per second, and 45 micron spacing in between each layer. The scaffolds were printed with our offset architecture, where every other layer is shifted in the XY direction by half its respective filament spacing. Again, filament spacing was the only thing that changed among scaffold groups. Scaffolds, N of 3 inks per group, were printed with 190, 260, and 400 micron filament spacings. A macroscopic image of a 195 filament spacing scaffold is shown in figure 2B. So, once printed, the scaffolds were punched using a circular 6 mm biopsy punch to obtain 4 punches per scaffold. Of those 4 punches, 3 samples per group were fixed to a glass slide and quasi-statically compressed using a custom-built microindenter. Regarding figure 3, scaffolds with lower porosity had higher compressive moduli, and scaffolds with higher porosity had lower compressive moduli. The compressive moduli for each group was statistically significant from each layer. Again, it's important to highlight this gives insight on how scaffold porosity affects stiffness, a mechanical property, which has an effect on cell differentiation. The remaining singular punches were characterized using scanning electron microscopy. SCM images were taken to confirm scaffold architecture via filament diameter and pore size. This was measured using 8 measurements per image and 5 images per scaffold punch, an N of 3 per scaffold group. Figures 4A, 4B, and 4C show SCM images of 190, 260, and 400 micron filament spacing scaffolds, corresponding to lower, middle, and higher porosity. For each filament spacing group, the filament spacing was confirmed to be statistically significant from each other. This was expected as the filament spacing is controlled by our printer codes, and different filament spacings were purposely programmed to achieve different porosities. This is seen in Figure 4D. Figure 4E displays the filament diameter, which is characterized to ensure scaffold architecture was consistent across all groups except for independently tuned filament spacings. There was no statistical significance in filament diameter among each group. This was also expected, as the same printing parameters were used for all scaffolds across each group. It's important to highlight that this information confirms that programmed filament spacings are being achieved and reflected in our scaffold pore size, and consistent filament diameter suggests scaffold architecture remains consistent, apart from the differences in filament spacings. As mentioned before, decoupling changes in cellular response is difficult because architecture mechanical properties are interdependent, but this data shows that differences in pore size can be achieved without affecting filament diameter, isolating any changes in compressive moduli to differences in scaffold porosity. In conclusion, I successfully 3D printed PCL scaffolds with different filament spacings and characterized them using microindentation and scanning electron microscopy. As expected, scaffolds with higher porosity had lower compressive moduli. In comparison, scaffolds with lower porosity had higher compressive moduli. I confirmed that filament diameter is consistent across all groups and scaffold pore size matched the programmed values. Further work includes culturing HMSCs in these scaffold groups under differentiation media to investigate how porosity affects osteogenic and chondrogenic activity.